Welcome to this video about the Reynolds transportation theorem. The idea is to describe the change of an integral quantity locally. So this means in computational fluid dynamics we have a lot of integral quantities where we would like to track the local changes, for instance mass, momentum or the energy. And this Reynolds transport theorem helps us to express this local change within formulas and then derive some physical equations like the Navier-Stokes equation and so on. For this, let's consider that we have a quantity which is a map from a volume and some time evolution to some real numbers, and the integral of it is like the following: that we have an integral quantity which is an integral quantity f of the time, which is integrated over the whole domain, so over the control volume, which we have here in the omega, of the local quantity. So it is usually a density, and yeah, it's integrated over the domain. Now we would like to track this temporal change. If we would like to track this temporal change, we simply apply the material derivative to the integral quantity, and then this populates in more or less that the material derivative is applied to the integral itself. If we now would use the Lagrangian reference frame for material bounded volumes, this would be simply changing the time derivative and the integral itself, so we can express this material derivative by a partial derivative with respect to time because we are in a Lagrangian reference frame, and then we could simply reverse the integral and the time derivative. And that was basically it in the Lagrangian reference frame. This means in a Lagrangian reference frame that the control volume is material bounded. So if the material deforms somehow, the control volume moves with the material, and then we can express it like this. But how does it look like in an Eulerian context? In an Eulerian context, we would have that this material derivative of this integral quantity itself acts or represents a local change, and then additionally we have a change or a flux across the surfaces, and this flux across the surfaces is also accounted for in the Eulerian context, because the control volume stays at a fixed position. And this is very much different from the Lagrangian thing, and therefore we have now the possibility to use integral theorem of Gauss and to include this surface flux term again into the volume integral itself by the divergence operator, and then we see that the surface flux term is more or less this convective term here. And that's basically it, that you can express the total change of an integral quantity by a local expression, which is this PDE expression here. And based on this this derivatives, we then can use this Reynolds transportation theorem for different conservation equations, which I will show you in the next video.